Okay, so I've got a thin-walled tube subjected to an axial force of 40 kilonewtons, elongates 3 millimeters, circumference decreases by 0.09 millimeters. Okay, I want to find the modulus of elasticity, Poisson's ratio, and the shear modulus. So the first thing I'm going to do is find the stress subjected upon this thing. So my stress is going to be force divided by area, where the force is 40 kilonewtons, divided by the area. And this is a tube, so it's outer minus inner, so it's going to be pi over, not pi over 4, because it's actually giving me the radius here, so I can just do pi r squared. So that's going to be pi 0.0125 squared minus 0.01 squared. Okay, so that gives me the stress equal to 226 megapascals, force divided by area. And now I need to find the strain, which is just the elongation, divided by its original length. So the elongation is 3 millimeters. The original length is 900 millimeters. As long as those two units match up, we should be good on that, which gives me a strain of 0.0033. Now from that, I can find my modulus of elasticity, which is just stress over strain. So stress over strain, so knowing the stress and its corresponding strain, I get 226 divided by 0.0033, and I get a modulus of elasticity of 67.9 gigapascals. Okay? Alright, so now the next thing I want to do is find Poisson's ratio. So I need to basically find the strain of the lateral strain. That is the strain of the radius, essentially. Now, it gives me the circumference difference. So we're going to start by my initial circumference, which is going to be 2 pi times, and I'm going to do everything on this one just in millimeters, just to keep too many zeros away, right? So that gives me a circumference. So the initial circumference is 78.54, and again, that's millimeters. Okay, and we know that decreases by, so my final is just that minus the 0.09, which gives me the 78.45 millimeters. And again, that's because I know the circumference decreases by 0.09 millimeters. Okay, so that means the radius, okay, 78.45 times 2 pi times my final radius. My final radius is then 12.486. Okay, so from that radius, okay, I can now find my latitudinal strain. That is the strain of the radius, just by taking the change in, so let me just write it, it'll be easier. So 12.5 minus 12.486, right? That's the change in the radius over the original radius. So that gives me this strain equal to 0.001146, and this is a negative strain. Why is it negative? Because it's shrinking. I probably should have done final minus initial rather than initial minus final, but just recognize that it's shrinking in size, so that strain is actually a negative strain, right? Because it's decreasing its radius. So from that, I can then figure out Poisson's ratio, okay, which is negative E lat all over E longitudinal, which is essentially what I've got up here, right? So plugging in those values, Again, I get negative, and I get negative 0.001146 divided by 0.0033, and I find that Poisson's ratio is 0.344. Now from those two values, I can figure out the shear modulus, okay, just from the following equation. So G then equals, on the denominator I have 2 times 1 plus Poisson's ratio. In the numerator I've got E. We just solved both of those, plug those in, and I get a shear modulus of 25.3 gigapascals. So again, remember Young's modulus is stress over strain within the proportional limit. Okay, so I get all that. Then I can find the lateral strain using the change in the radius. Once I get that lateral strain and the longitudinal strain, I can find Poisson's ratio. Once I know Young's modulus and Poisson's ratio, I can find the shear modulus.